Welcome to this video in the acid-base chapters. This is 15.1. Today we're going to talk about the Arrhenius and the Bronsted-Lowry theory of acids and bases, as well as teach you guys about conjugate acids and bases and their strength relative to one another. If you haven't already done so, please make sure you have downloaded and printed your companion worksheet for this video lesson and have your New York State CSRT handy. We are going to take a peek at that a couple different spots. So without any further ado, let's get started. So this video is going to begin by talking about the two most prominent acid-base theories that you guys will need to know for your Regents exam. That is the Arrhenius theory and the Bronsted-Lowry theory. You may also see that Gilbert Lewis is here, he of the Lewis dot model fame. But in this video, we are going to withhold talking about Lewis, and we may hit it in class if we actually have some time. So Gilbert, we hardly knew you. So in talking about the Arrhenius theory, you can't help but mention Mr. Svante Arrhenius, who in 1887 proposed this amazing acid-base theory. He actually won a Nobel Prize in 1903, and he actually wasn't studying acids and bases at all. He was really studying the dissociation of substances in water, which, if you do think about it, does make some sense as to why he would propose an acid-base theory to begin with, because acids are dissolved in water and are aqueous solutions. So anyway, let's talk a little bit about what he said. The Arrhenius acid is anything that would release a hydrogen ion in an aqueous solution. So if you have something and you put it in water and hydrogen ions are released or liberated or come free, he would have classified that as an acid, or in our case, an Arrhenius acid. Typical examples of that are classic acids that you would see here: hydrochloric acid, nitric acid, sulfuric, phosphoric. And what you see is, this is the first time we may be mentioning this, these guys here are examples of monoprotic acids. Monoprotic meaning one hydrogen or one proton. We'll talk about that in a second. These are diprotic, here's your 2, or triprotic, there's your 3. If I look at the animation that's down here, we see HCl, and we do see a water molecule. And what we notice is that as that HCl collides with the water molecule, the hydrogen is liberated or freed or released, and it gets picked up by the water to form H3O, otherwise known as hydronium. That is a main player in this unit, and we will certainly talk a lot more about hydronium. Looking at the dissociation equations, we can now start to make sense that if you ever saw something like this, where you saw, let's say, HNO3 in the presence of water, that would release the hydrogen ion and would also release a spectator ion here of nitrate. The fact that it released a hydrogen ion would classify it as an Arrhenius acid. We don't really care about the anion here. It doesn't make a difference in terms of the acid classification. And same with these here. The sulfuric acid releases 2. That's what makes it an Arrhenius acid. The phosphoric would release 3, making it an Arrhenius acid as well. Now, if you happen to forget the definition of an Arrhenius acid or what the examples are, fret not. New York State's got your back. This is Table K. You'll notice on Table K they have listed a bunch of different acids. That's pretty cool. When you look at this, you may be saying, as you scroll down here, wait, this bottom one does not begin with an H, but yet the other ones do. Well, that's because this is acetic acid, and acetic acid, actually, the hydrogen ion gets released from the tail end of this. This is an organic acid, whereas the rest of these are inorganic. So Table K is a nice cheat sheet for you to have, and the best part is New York State is gonna give it to you, so don't forget. Arrhenius didn't stop there. He actually had a theory of bases as well, and he said bases are substances that will release hydroxide ions in solution. That is the OH-, which you guys have seen many times on Table E. If you look at the animation here, you could see we do have indeed sodium hydroxide solid, and they're not showing the water here with this, but it is dissociating into sodium ions and hydroxide ions. The fact that the hydroxide ion is liberated when it dissociates in solution is what makes it an Arrhenius base. And you can see that written here. Here are 3 dissociation equations For the three bases that are listed, you'll see in addition to the positive cation that is liberated when it dissolves in water, you do see multiple hydroxides that come off on the magnesium hydroxide. You see one that comes off of the potassium hydroxide and one that comes off of the sodium hydroxide. But it doesn't really matter if it releases 1 or releases 15. By releasing an OH in solution, that classifies it as an Arrhenius base. So just like we had a cheat sheet for Arrhenius acids, bam, we got a cheat sheet for Arrhenius bases as well. It is the mighty table L. If I look at this, I see sodium hydroxide, potassium hydroxide, calcium hydroxide, and aqueous ammonia? Wait a second. I know you guys are sitting there going, dude, there's no hydroxide there. But yet it's on a table of common bases. Does that mean that New York State went wrong? I mean, entirely possible, but let's look at the properties of aqueous ammonia and just make sure that it's a base. Aqueous ammonia would turn litmus paper blue. Since elementary school, you have known that that is one of the properties of a base. It neutralizes acids. That is one of the properties of a base. And it behaves as a base in all other ways. It probably tastes sour, though please try not to do that at home. So it doesn't really abide by the Arrhenius theory. So guess what? This is one of those spots where we actually had to take the Arrhenius theory and say, it's really good for some things, but not others. We need an alternative. Enter Bronsted and Lowry. Johannes Bronsted and Thomas Lowry. One was a Danish chemist, one was English. Now, you may think that they were working together, but they were not. It was independent work, all happening at the same time. So maybe there was some shenanigans, tomfoolery, malfeasance, and skullduggery, but nonetheless, they named it after both of them. Now, New York State is not going to refer to it by its God-given birth name, the Bronsted-Lowry Theory. They're going to call it the alternative acid-base theory. So, I don't know why. Maybe it's trademarked. But let me tell you a little bit more about it. According to Bronsted and Lowry, their theory is different than Arrhenius because they say acids are hydrogen ions, or as they call them, proton donors. Why are they protons? Well, you know, if you're a hydrogen ion, you've lost your electron and you have no neutrons to begin with, so all that's left is a proton. So the yin to the acid yang is the base. The Bronsted-Lowry theory says that bases are proton acceptors, or hydrogen ion acceptors. So the acids donate the hydrogen ion and the base is accepted. It's super easy. Check this example out here. Here we have ammonia, which is a base, and it is reacting with water. In terms of acid-base theories, you guys will think back to all the times I said, be careful, water's an acid. Well, this is a case where it is. It's a Bronsted acid, and this is a Bronsted base. Now, why is this a Bronsted acid? Well, the water is a Bronsted acid because it is donating a hydrogen to the base, which is accepting it to form ammonium, NH4+, and the water lost or donated the hydrogen to form hydroxide. So why ammonia is considered a base on the table of bases in your CSRT is because it actually does create hydroxide ions that will drive the pH somewhere above 7, except it doesn't make it directly. It happens as a result of the water losing that hydrogen ion or donating it and being left with just a hydroxide ion, and that's what's really driving the pH above 7. And that is the Bronsted-Lowry theory of acids and bases. So now that that's in the books, I want to bring up something called amphoterism, or what we call amphiprotic substances. I'd like you guys to take a look at the two water molecules that are smashing into one another. What do you guys notice? If you look closely, you'll notice that one of these waters is colliding with the other water and donating a hydrogen, while the other one is accepting the hydrogen, which would technically make these two water molecules Bronsted acids and bases. Now, being amphiprotic is not just reserved for water. There are plenty of other substances that can accept or donate a hydrogen. We'll get into a little more of that later. While here, I also want to briefly touch upon hydronium. Now, you're going to notice here it says H plus versus H3O. One of the things you have to understand is that whenever you have a hydrogen ion that is released in water, a water molecule will ferociously and super quickly pick it up. Why? Well, hydrogen ions are positive And you guys know that water is a polar molecule with a very, very, very negative end to it where the two lone pairs are on the oxygen. So what we see is this interchangeable use of hydrogen and hydronium. They represent the same thing. So if they are talking about an acid having a high hydrogen ion concentration, they could also say the acid has a high hydronium ion concentration. So just be aware, hydrogen ions and hydronium ions interchangeably describe the ion that an acid will release in water. Important that you guys get that. Okay, moving on. So the last thing that we are going to get to today is what are called conjugate acid-base pairs. And a conjugate acid-base pair is pretty simple if you understand what's going on using the Bronsted-Lowry theory. Now, first fact is that conjugate acid-base pairs differ by a proton. Well, what exactly does that mean? Well, let's now look at the reactants that are here. Here we have HA representing a generic acid, and here we have B representing a base. According to Bronsted and Lowry, this is your proton donor here. This is your proton acceptor. You will notice that when this acid donates the hydrogen to this base, what is left over here is simply this anion, or what we're calling A-. This is our conjugate. So the acid donates its hydrogen and then forms what is known as the conjugate base. The base accepts the hydrogen ion and then forms what is known as the conjugate acid. If you look at it with real acids and bases down here instead of just the letter examples, you'll see here's HNO3, that's your acid. It's going to donate its hydrogen, and what we're left with after that's donated is NO3. So that's your conjugate base. So the pair is HNO3 being the acid and NO3 being the base. The base is hydroxide. It's going to accept the hydrogen ion and form water. So the pair is hydroxide and water. So conjugate acid-base pairs will always differ by one proton. One way you could think of it is that the acid will always have one more hydrogen than the conjugate base will, and the base will have one less hydrogen than the conjugate acid will. So one side note that we need to be aware of is what we call the strength of acids and bases and their conjugates. So it is a little complicated as to why it happens. I'll certainly get into that with you guys in class if you have questions about it. But in the meantime, we just need to understand the relationship that if you have strong acids and bases, they will yield weak conjugates. And conversely, if you have weak acids and bases, they will yield strong conjugates. So, for example, we know HCl is a strong acid. That means its conjugate base, which in this case is Cl-, is going to be considered weak. So make sure you pay attention to that relationship. It'll come in handy, and I can certainly talk through why in class. So what I want to do now is give you guys a problem for practice. Here is an equation. It's an acid-base equation. I would like to see if you can stop the video and identify what the acid is, the base is, the conjugate acid, conjugate base, and underneath, please tell me what the acid-base conjugate pairs are. So stop the video now and then start it again when you're ready for the answer. Okay, if you did this correctly, here's what you should have gotten. We should have had HOCl as our acid, OCl-1 as the conjugate base, and NH3 as our base, and NH4 plus as our conjugate acid. You'll notice my acid and conjugate base pairs. Here are HOCl and OCl-1, and my base and conjugate acid pairs are NH3 and NH4 plus. Make sure you make a note if you have any questions about this. We can talk about it during the burning questions segment tomorrow. Here's another one. Now, I'm giving you the identity of an acid and the base. You tell me the identity of its conjugate. And to remind you, at the bottom we have a hint. Remember, conjugate bases have one less hydrogen than the acid does. And conjugate acids always have one more hydrogen than the base does. So pause the video now, fill this chart out, and then unpause and see how you did. Okay, if you did this correctly, here are your answers. Remember, if you keep getting these wrong or you have a problem with anything that you understand, you could certainly talk about it tomorrow during our Burning Questions segment. Okay, it's time to say farewell to this lesson on acid-base theories and conjugates. It has been a pleasure being your teacher, and once again, always remember, if you had any issues with anything, we can certainly talk about them during the Burning Questions segment tomorrow. I will see you on the flip side. Peace out.
That's all, folks.